want to talk about the content that we're covering in the calorimetry unit. I'm actually going to make two videos on the content. This is the first one. It's going to cover what you see here. There'll be a second one that covers the latter half, which deals with methods of heat transfer. Let's jump right into it, though, with the calorimetry statement. And you can see it up here on the right in bold. The temperature and phase of an object cannot simultaneously change. So this means if something is changing temperature, so for example, maybe you're heating up an iron, okay? Well, while it's heating up, its temperature is changing, its phase is not. The iron is still solid. It isn't melting and becoming a liquid mess. It is still solid. So its temperature is changing, but not its phase. If it's changing phase, then its temperature has to remain constant. A great example of this would be an ice cube. Ice melts at 0 degrees Celsius. So if it's a hot, blazing summer day, 100 degrees outside, 100 degrees Fahrenheit, and you take an ice cube out there with you and it's in your hand, it will, of course, start melting in your hand because it's so hot outside. But it's not like the ice cube itself is suddenly going to get to a nice warm temperature. It's not going to get up to 70 degrees Fahrenheit or 80 degrees Fahrenheit. It's going to be cold in your hand the whole time it's melting because it's changing phase and it melts at 0 degrees Celsius. So the whole time it's melting in your hand, that ice cube is at 0 degrees Celsius. Its phase is changing, so its temperature remains constant. Another example is boiling water. Water boils at 100 degrees Celsius. This is why directions for a lot of pasta products, etc., a lot of little meals that you can purchase at the store, when you're looking at the directions, one of the first things it says is to boil water. Why? Because they know that water boils at 100 degrees Celsius. And so they know if you get that water boiling, it's going to be at 100 degrees Celsius, and then you have to cook the pasta for like 10 minutes, and then it's good to go. They could say something like, oh, get it up to 70 degrees Celsius, but they don't know how attentive you're going to be. Are you going to make sure it's exactly at 70 the whole time, for the whole time it's cooking? They can't guarantee that, and they want to make sure you buy their product, so they're trying to make it as easy as possible. Anybody can boil water, so they just say, look, boil the water, do it, put the pasta in, 10 minutes, you're good to go. So it makes it easy, and of course, this all works because water is changing phase at 100 degrees Celsius, is boiling, and so consequently its temperature remains constant. That's the key idea here that we are dealing with. Now, I've already started talking about phase changes. There are three common phases. We've got gas, liquid, and solid. There are many, many different phases of matter. I think the last time I checked, there were over 30 that have been identified. Okay, maybe I'm wrong, maybe I'm misremembering, but it's a bunch. But we're only going to focus on the three common ones: gas, liquid, and solid. And you can see in this chart here, it's got the phase changes indicated. You can go from gas to solid, or solid to gas to liquid, etc. And you're probably familiar with most of these phase changes: melting, boiling, sublimation, freezing, condensation, and deposition. The two you might not be familiar with: sublimation and deposition. Okay. Deposition, a good example of this is frost. Okay. You've got water vapor in the air, and under the right conditions, it goes straight from being a water vapor to being solid, to being ice. Sublimation, a good example of this is dry ice. That's solid carbon dioxide. Under the standard conditions that we live in, you can't have liquid carbon dioxide. That means if you get a solid chunk of dry ice, if you get some dry ice, then if you throw it in some water, when you heat it up, it's going to go straight from solid to gas. And you see dry ice a lot, like at Halloween, because that's what produces that fog. People throw it into buckets of water or something, and it gets kind of foggy that comes out. That's because of dry ice. Now, these top three require heat to enter the object to occur. Heat must enter the object for melting, boiling, or sublimation to occur. These bottom three, heat must leave the object for these to occur. Freezing, condensation, and deposition, heat must leave the object for these to occur. Now, thermal equilibrium, we've already talked about, but I'll just quickly mention it again. Two objects are in thermal equilibrium if they have the same temperature. And one thing we will be talking about or making reference to in this unit is we'll talk about the equilibrium temperature. And so that, of course, is referring to when the system, everything in the system has reached thermal equilibrium. So now we're getting to the meat, the formulas of this unit. And we've got two big ones here. Q equals mc delta T and Q equals plus or minus ml. This first one is dealing with heat due to temperature change. We're using Q to represent heat. M, of course, is the mass of the object. C is known as the specific heat. Okay, it's got units of joules per kilogram Kelvin. Okay, that's the correct MKS units right there, joules per kilogram Kelvin. And specific heat is the measure of a substance's resistance to temperature change. Some materials readily change temperature. You give them just a little bit of heat and their temperature will change quite a bit. Metals are a good example. Metals tend to be good thermal conductors. You give them a little bit of heat, they change temperature readily. Other materials, not so readily. And so you have to give them a lot of heat to get their temperature to change. So things that, like metals that change readily, they have low specific heats. Things that do not change temperature so readily, they have high specific heats. Sometimes specific heat is also mentioned or referred to as thermal inertia. Delta T is the temperature change. You can use Kelvin or degrees Celsius because a temperature change of 1 Kelvin is the same as a temperature change of 1 degree Celsius. And so this is our formula for the heat due to a temperature change. So if the temperature changes in an object, we can calculate how much heat is involved, or if we know we're giving heat to an object, we can figure out, say, how much the temperature changes, or the specific heat, or whatever it is we want to know. Now this other one, heat due to a phase change. So if a phase change is occurring, well, then we just need to know the mass and the latent heat. This L here is the latent heat. It's the measure of a substance's resistance to a specific phase change. So that means it's not just dependent on what the substance is, but also what phase change is occurring. Now, the ones that are between the same two phases, so for example, gas to liquid or liquid to gas, that's the same latent heat. If you're going between these two phases, it doesn't matter which way you're going, it's the same latent heat. If you're going between these two, there'll be a single latent heat but going between gas and solid, and a single one going between liquid and solid. But what you really have to pay attention to is this here, the plus or minus. How do you know whether to choose the plus or the minus? That depends on which phase change is occurring. If it's one of these three, it's going to be the plus. If it's one of these three, it's going to be the minus. You have to choose, so you have to pay attention to that. The last thing is this down here. This is conservation of energy with only heat exchange. Now we're dealing with calorimetry here, so we're dealing with, calorimetry just refers to heat exchange. Heat is just a form of energy. It falls into that category of thermal energy that we've been talking about ever since we started talking about energy. And we can certainly talk about conservation of energy in terms of delta KE plus delta PE plus delta TE. And indeed, you have a problem or two that deal with this. But there's a lot of situations where you really don't have any significant change in kinetic energy or change in potential energy. And there's really, the only thing that's going on is heat exchange. Okay. And so in those situations, we're going to be making use of this expression here. The sum of the individual Q's has to equal 0. So how do you use this? How do you use this formula that we have here? Well, it depends on how many objects you have. So for example, if I'm doing this, if I have three objects. So maybe I've got a cup of water and I put some ice in it. So that's three different objects. I've got the cup, I've got the water, and I've got the ice. So then I've got to have Q1 plus Q2 plus Q3 equals 0. And so 1 might be my cup. So what's going on with the cup? Is the cup changing temperature? I mean, that's all the cup should do, so that's all I would worry about, the MC delta T. The water is probably just changing temperature, so that would be some kind of MC delta T. The ice, okay, now the ice is probably melting, so that gets more involved because it's going to melt, it's going to turn into water, and that water itself is going to heat up. That gets more involved. And I look at those details in another video in front of one of the problems that is dealing with that very kind of situation where you have an ice cube that's melting. But that's all I wanted to say right now. Again, down here, this bottom equation, you have as many Q's as you have objects in your system. If you have 3 objects in your system, then you have 3 Q's, and then you have to analyze each one to figure out which formula, or perhaps a combination of formulas, you are going to use for a specific Q in this formula.